The graph below is the function f of x. Okay. This function is not continuous at -1. Correct. There is a jump discontinuity. I can see that very clearly in the graph. Determine which one of the following rules for continuity is the first that is violated. Huh? When a equals -1. Okay, I didn't know there was a chain of events that had to happen with regard to continuity. Let's see. The limit does not exist. F of a is defined. So f of a is defined, so it can't be that one. I think it's this one, right? The limit does I'm gonna pick this one. The limit does not exist. We have a left-sided limit tending towards -3, and we have a right-sided limit tending towards +3. So the limit doesn't exist. But the function is defined. The function evaluated at -1 is +3. So I think this is what they're going to want for question number 1. Okay, what's going on here? I think in a similar fashion, we are going to say that this function is defined. It's defined here. I can see that. Its limit exists, right? The left and right-sided limits exist. But the problem here is that the limit that we get is going to be -2, but the function evaluated at 2 is -1. So these two things aren't going to quite line up, and that's going to cause this discontinuity on us here. At x is equal to 2. Okay, so we have a function. Show that f of x has a jump discontinuity at 8 by calculating the limits from either side. All right, we can do that. So when x is less than 8, so we can take a limit as x approaches 8 from the left. We should be able to look at this piece of our function, this 6x minus 6, and we can go ahead and substitute 8 right in to get 6 times 8 minus 6, which is 48 minus 6. Is that 42? So as we approach 8 from the left, we get 42. And we want to do the same thing on the right side. So we want the limit as x approaches 8, but for values slightly bigger than 8, we can use 2 over x plus 6. Again, there are really no issues here, so we can do a direct substitution because 2 over x plus 6 is continuous. So 8 plus 6. So we get 2 over 14? 1/7? So there we go. We get 2 different limits from either side. So because those limits don't match up, we have some kind of jump discontinuity happening. Very similar to what we had in the previous question, right? When we were kind of graphing it back here, right? So these absolute values sometimes have jump discontinuities where the limits exist, but we just can't get them to line up properly. Okay, Desmos can help us a little bit here if I remember how to plot a piecewise function. How do I do a piecewise function again? I need the, it's always backwards to what I think. I think it's like I need the region, and then I need the x squared minus c, and then I go comma, and then I go x bigger than or equal to 6, semicolon cx plus 9. And then we'll add a slider, and here we go. So here's what our function looks like using Desmos. And we can see that there's a jump discontinuity here. But I should be able to adjust different values. Oh, interesting. So I can adjust the values of C. And what we're trying to do is we're trying to get these pieces to kind of line up and kind of clip together like right around there somewhere. Somewhere in here. So somewhere in the like C equals 4 neighborhood, maybe? No, 4 is too big, 3.5. That's too small. Nope, 38, 3.8. I don't know, it's gotta be somewhere in there. It's like around 3.8, like it's pretty close. 7.5, like 3.75 is close, but it's not quite close enough. So I need these two things to line up. What am I getting up here? It's like some weird number. What's this? Okay, so let's see if we can figure this out algebraically. So what we need is we need the limit as x gets close to 6 from the right to be equal to the limit as x approaches 6 from the left. So we want to make sure that this jump discontinuity does not happen. For values that are slightly bigger than 6, we can use this one. And for values that are slightly smaller than 6, we can use this one. So for bigger than 6, we can use cx plus 9. And for slightly smaller, we can use x squared minus c. So that's setting it up algebraically. Fem says 27 over 7. Okay, let's see. That's a very oddly specific fraction, so it's probably right. So if I sub 6 in for x, I'm going to get 6 c's plus 9. And if I sub 6 in for x over on the right-hand side, I should get 6 times 6, which is 36. Take away c. So yeah, altogether I'm going to have 7 c's if I move this negative c over, and then we get 36 take away 9, which, yeah, is 27. So that's correct. C is 27 over 7. Well done, Fem. Nicely done.
Easy as pie.
And if we head back to Desmos, we can hopefully verify that that is true by just updating this to 27 over 7. And as we zoom in to that function, we can see that things are a little funky, right? There's like a little bit of a corner bend in there, but everything looks like it lines up, and I can see that the dot goes smoothly over both pieces of this piecewise function. So yeah, that looks good. That looks good from a geometrical standpoint. Nice. I love those questions. I think those are such fun questions. So given the function below, determine if the function is continuous at -4. If not, indicate why. So like we were doing before, we just want to make, well, I mean, it's not defined at 4, or -4. I mean, we could just go to here, I guess. This function isn't even defined at -4. There's no way that this can be continuous at -4 if it's not defined there. Given the function below, determine if the function is continuous at -1. If not, indicate why. Wait, this function's not defined at -1, right? This function's defined everywhere except -1, isn't it? X plus 1? What do you want from me? Use parentheses around the argument. Okay. Yeah, what a weird looking function.
Stay in your lane, please. I'm on a whole Zeta level above you. Math, it's art, and I'm the master. Focus on your own skills before critiquing the genius.
Math is art. That was funny. Yeah, so this is not defined at -1, so I think we're going to run into a similar problem here. It's not continuous there because f at -1 is not defined, so it's got to be one of these two. Which one do we think it is? So it's got to be one of these two. F at -1 is not defined. This is a removable discontinuity, or this is not a removable discontinuity. I feel like I'm going to go with this one. I feel like I'm going to go with this one. I don't think when we have a weird asymptote like that, it's a removable discontinuity, but I could be wrong. Yeah, I think so too. I think so too, lads.
Nicely integrated.